All right. So this is a published paper recently, and so the reason for why one needs cost-efficient evolution models is that one has several astrophysical applications that require it. So first of all, large-scale simulations of, for example, galactic evolution, then stellar and body dynamics codes, rapid population synthesis, and also the inference on stellar parameters from observations, which typically require millions of evaluations for convergence to the best fit model. And what I've done is I've taken a set of solution tracks pre-computed with the MESA code from the zero event sequence up to the end of coherent burning phase, thereby covering more than 99% of their lifetimes, and over a mass range from sub-solar mass red dwarfs up to 300 solar mass Wolf-Rayet stars. And you see the tracks in the Hershey-Russell diagram and the Gill diagram plotted for unseen masses of by the machine learning model, and then the predictions of the machine learning model at these parameter locations. And a few words on the model behind this. So I set up a two-step scheme where one goes from the age and mass of a star to a latent variable, which quantifies the evolutionary state of a star. And then this is used in the second step instead of age to predict the stellar observables. And as a best fit model addressing this regression problem, I found a feed-forward neural network, which I hyperparameter optimized. And this figure illustrates how this works. And on this slide, I tell you about what this latent variable is. It's a timescale adaptive evolutionary coordinate, which is used to reparameterize evolution of stars. And you see the need for this when you look at the time series of log luminosity of a sun-like star from the zero event sequence up to the end of coherent burning phase, and during the late stages of its evolution, the final 10%, the star undergoes substantial changes. And in order to get high accuracy fits, you cannot do that directly in time domain, but using the reparameterization that I introduced, one can resolve the different features like the first branch up, the tip of the right giant branch, the contraction of the envelope, the sequence of helium flashes until the star finally settles on the horizontal branch. So that's the first project. So the second project, the title is Supervised Learning-Based Template Construction for Gravitational Waves from Neutron Star Merger Remnants. And it's a soon-to-be submitted paper where I'm second author. The goal of this was to construct a matched filtering template for gravitational waves from the post-merger phase of neutron star binaries. That could be used in a real case detection scenario where one has data provided by the LIGO-Virgo interferometry at advanced sensitivity, and then the templates being scanned through it in order to search for signals. And the motivation behind this is that once one detects the gravitational waves away from the post-merger phase, this will allow to constrain the equational state of neutron stars and the high density region. So just an illustration of the matched filtering technique works. And to this end, the first author has run general relativistic simulations of binary neutron star late in-spiral merger and post-merger phase. And as the post-merger is sort of having a time variable mass quadrupole moment and is stabilized by differential rotation and thermal effects, it emits gravitational waves, which carry information about the interior structure of the neutron star. And so my role was to take the gravitational waves that have been emitted meanwhile and put them together and parameterize them as a function of source parameters, and to construct a template that generalizes the prediction of waveforms over the entire parameter space. And there are two steps that have been crucial for success. So the first one was the alignment of rotation waves in phase, such that the peak amplitude is sort of aligned over the first millisecond, and then a model that's appropriate model choice that allows to address the regression problem in time domain. And you see here a prediction of a rotation waveform for an unseen total binary mass and a fitting factor that assesses the predictive quality. So the simulation, the true gravitational wave signal is in white, and in blue is the model prediction for an unseen total mass. And yeah, this is the distribution of fitting factors, which are used to quantify the performance over the entire total binary mass range, where the minimal mass is set by the assumption of minimal neutron star mass at birth in the core collapse supernova, and the maximal total binary mass is set by a threshold mass at which one observes prompt black hole formation from the neutron star major remnant. And along with the total mass, also the mass ratio has been varied. And our performance baseline was that over the test data, so unseen cases, the gravitational waveforms are predicted with a fitting factor that is not worse than 0.8, which is enough to claim detection. And this is what we observe here. And we also verify robustness against noise in an injection study using the Bilby package to infer the source parameters. Yeah, I guess just quickly on the fine project, which is in prep paper, effects of convective core overshoot assumption on compact remnant mass and type 2 supernova explosion energy landscapes from massive single star evolution. So convective core boundary mixing is one of the major modeling uncertainties of massive star evolution, which directly impacts the course of the star and thereby their final fates and remnant properties. And there is observational evidence that the extent of the overshoot zone increases with increasing mass. And recently, a grid study has been done with MESA, running cell evolution models from 9 to 50 solar masses at different fixed overshoot values, and up to the onset of iron core infall, and then the semi-analytical Müller model applied to obtain the final fates. And so I've constructed explodability and fallback proxies that allow to generalize these predictions over the entire parameter space. And this then allowed to this is just an illustration how this works. One predicts one of the variables that I'm using for the explodability proxy as function of mass of the carbon oxygen core and step overshoot parameter. The red points are the actual data points from the numerical code, and in blue is the generalization made by the Gaussian process model. And in gray, the plane shows the maximum specific entropy above which all the progenitors collapse to form black holes. And then once one has the final fates, one can compute a new distribution of remnant masses, assuming a prescription for overshoot that scales with mass. You see the neutron star mass distribution, the first black hole masses peak, and the neutron star black hole mass gap polluted by two fallback black hole islands. A gap in the black hole mass distribution and onset of the black hole plateau, which then in theory continues up to the parent stability mass gap. And for comparison, the explosion energy landscape, assuming a fixed overshoot, and so peaking at about 0.86 in beta units, and with having a long tail towards the high explosion energies. And yeah, that's essentially just a quick summary of what the advantages are and what applications are possible with supervised machine learning. Thanks for bearing with me with technical problems, and I'm happy to take questions.